Hello, everyone. Welcome to the Finance Track at AI Forward 2021. Please give a warm virtual round of applause to Mike Purewal. Mike, welcome to the virtual stage.
Thank you, Dan. Very excited to be here. I'm going to go ahead and share my screen here. As Dan mentioned, my name is Mike Purewal. I'm a front office data scientist at Bank of America, where I'm actually implementing machine learning models that drive value for our clients. I'm also an adjunct professor at NYU, where I teach machine learning and finance. And today's talk's really about my experience as a practitioner in the space, implementing models on financial data, which are inherently very noisy. Specifically, I'll be talking about best practices when dealing with imbalanced data. And from my own point of view, I noticed there's a bit of gap in the literature on imbalanced data sets in the ML context in finance, right? And so the goal here is to remix some known concepts across different, and this will generate some novel insight that I hope will benefit you. Let's go to the next slide here. In terms of specific takeaways, so I tried to appeal to the general audience. I know it's a varied audience here at AI4. And I think if you're going to be a successful data scientist anyway, you need to put yourself in the shoes of all your stakeholders, right? It's a very important step. And so if you're an executive or a business owner, what I want you to take away from this talk is you should be getting excited about the power of machine learning to help your business, right? Finance is a very vast subject, and you might have to draw some parallels and do a bit of stretching to see how the content directly applies to you. But the fact that it's finance driven takes you most of the way there, right? So if this talk was, say, about self-driving cars, it might be too big of a stretch to apply to you. But here we're dealing with mostly finance concepts. If you're a trader, or more generically, you're a product person, this is about giving you the language to articulate your needs, right? In my experience, I see a typical conversation between a trader and a data scientist go like this. The trader says, hey, give me a model that predicts Y. And then the data scientist says, okay. And they go away for several weeks at a time, right? At worst case, they go away for longer. And they come back with a model. That's not a healthy conversation, right? It's like a person going into a wine store and saying, I'd like some wine. Too generic of an ask. It leaves too much to interpretation. And this presentation at a minimum should help you be able to say, hey, I want red wine or white wine, right? These are a subset of your problems. And then finally, kind of where this talk is really bulk directed towards is for data scientists, right? This should help you be the tools to model imbalanced data sets and kind of clean up your overall, what I call model hygiene. So let's dig in. Let's start by looking at some different types of imbalanced data problems in finance, right? As I mentioned, they're varied and they're pervasive, right? They're everywhere in finance. But from a modeling perspective, there's a common thread in how they're handled. So going row by row here, the first row we have credit defaults, right? And the size of your data set is typically the number of companies you have, which is on the order of 1,000 or 10,000, right? And your event size, or your signal, is really around 1 to 10%, right? 10% very high number, but it's in that range roughly. In the second row, when you're dealing with consumer defaults, you kind of increase your data set by an order of magnitude or several orders of magnitude, depending on who you are. You might have 100 million different consumers, credit card holders, and so on. And when you deal with non-payments, you're dealing with 1% or 10%, right? So these are imbalanced data sets. They're mostly non-defaults, but they're sprinkled in some events you want to detect. Fraud detection, another big one. If you're thinking about credit card transactions, globally, there's 1 billion every single day, right? And a very, very small percentage of these are fraud. A space near and dear to me, trade executions. When you think about requests for RFQs, it could vary depending on your asset class, your platform, et cetera. But clients typically ask for way more quotes than actually execute, right? So that's your imbalance, kind of their executions are less than 1%. And then finally, if you think about trade recommendations, another ML use case I've seen in finance, you're trying to recommend a security, again, depending on your asset class, you might have about 10,000 securities. And the goal here is to recommend a very small, palatable subset of those, less than 1%, right? So these are the different use cases. And, the modeler can use machine learning to make predictions in each of these realms. But this talk covers some of the specific best practices when handling these types of problems. The first suggestion we have here is, you have to get the problem stated in completion. So even if the goal here is the data scientist works on a very small component of a more general problem, having a clear vision up front of what is overall the ask is very important. So as an example is in the case of credit losses, which kind of serve as a running example in this talk. The ask might be for the data scientist, hey, predict whether the company defaults or not, right? And that's what I have represented here in the left-hand side on the upper panel. You might say green is no default, red is default, right? A binary outcome. But that's not what the end user typically uses default for, right? What they ultimately want are losses in the event of default. How much will I lose when a default occurs, right? Or there might be some other downstream business metric, right? But ultimately, knowing whether they're going to default or not is not sufficient. And all of this should be upfront because it has very important and subtle implications to the modeler. Another example is if you think about trade or security recommendation. Perhaps the ultimate business metric is not whether a recommendation is acted on, but what is the average spend if the trade is recommended, right? And so, the ask here is make sure you state the full problem and so that the modeler is aware of it. Why is it important to state this ultimate objective? Because from an implementation perspective, data scientists are trained and taught that you can swap a few lines of code out and you can accommodate the different output. In fact, machine learning APIs, they've made them very simple to transition one output from the next. But that's very misleading to say it's easy to implement because it's not necessarily the right thing to do. The more experienced quants know that it's important to have an eye on the end game. So ultimately, you're using the right tools to begin with. So at the bottom of this particular slide, we're showing that the first ask might be a binary prediction case. So you want to identify the hyperplane separating the classes, and that's all they ask for. So let's say, orange is the dots at the orange are your defaults, and your non-defaults are in blue. The red line is the hyperplane that separates the two classes, right? And that might be the idea of binary ask. Can you identify default or not default? However, if we want to use this calculation downstream for deeper modeling, what ultimately occurs is we need the probability, which is a slightly different ask. So a data scientist might tell you, hey, this is a few lines of code. You just swap in the dot predict with a dot predict proba. That's sklearn talk in Python, if you're not familiar with it. And it's true, but it actually misses some of the mathematical subtleties. So that's suggestion one, define the end game, state the problem very clearly. Once you have this requirement, the second suggestion is modularize your models. You want to break the problem, the general problem, into a set of smaller estimations. And there's two main reasons for this. One is you get better estimation. Two is you get better model hygiene. And I'll explain what each of these mean. For better estimation, if you're not familiar with Fermi estimation, I have a link over here. You could take a look on Wiki, just Google it. Enrico Fermi, famous physicist, did theory and an experiment. He's known as the architect of the nuclear bomb. And he was also known to estimate complex calculations using back of the envelope kind of type calculations. And he broke them up into smaller components. The high level idea is that if you're roughly right on each of the smaller computations, the aggregate prediction error is much smaller. The errors tend to cancel out. And that's why instead of trying to model it in one chunk, you actually want to try to break it into smaller components. The other benefit, which is what I call model hygiene, what you gain by modularizing your calculations is your code becomes more maintainable, right? You also get the ability to reuse and replace the components. I have an example below here in this diagram on credit loss modeling. Generally, you have credit risk and it's broken into different components. Won't get into the details there, but each of these components can be calculated in different ways. Instead of calculating the loss in one shot, it's broken into subcomponents and then combined in a way that's mathematically equivalent. So in this example here, if we're very good at predicting the default probability of an event, but we're iffy on exposure prediction, then perhaps what we want to do is to start with, a past average behavior, what I call exposure model A, right? This lowers our time to market because we aren't looking for a sophisticated model here. And it gives us some time and runway for the developer to increase sophistication and improve the model. Say, move to model B and C, which is like maximum likelihood or machine learning. It also provides a benchmark to measure the benefit of sophistication and moving down that value chain. Finally, you could potentially use these subcomponents elsewhere, right? That's a reusability aspect of this model hygiene. So perhaps you actually want to use your probability of default or PD model in a completely different place. And that's why that arrow goes to a different location, right? It gives you these Lego blocks, which you can use in different locations. And all this is possible by modularizing your calculation. So how do we model these imbalanced data problems? Right, let's get into some of the details here. And we're going to stick with this credit example. One of the challenges in discussing financial data is it's so hard to share it. So I've generated some data and, tried to illustrate some of these concepts with made up data. And the idea is you can extend this to pretty much any use case that's imbalanced in nature. The idea is the same. On the left-hand side, when you're dealing with imbalanced data, most of the time, nothing happens, right? Nothing happens. And that's represented on the left-hand side by that spike next to $0. It's saying there's a large amount of zeros because defaults are rare, right? And if you want to model losses or size of trade executions or spend, the zeros dominate your data and it's hard to see any signal. A new data scientist, what they're trained to do is model that left-hand side directly. It's called the unconditional distribution. That's a technical term. In the non-ML case, right, in the traditional quant approach, there's a standard technique that we should all bring to the machine learning world, and it's called modeling conditional distribution. You essentially remove all the zeros and get a cleaner view into the signal. That's what we have on the right-hand side. It's the same as left-hand side, but we've removed the zeros and we have a different scale. So take a look at the axes there. And this is called the conditional distribution. It's that underline of that I have in orange underneath in that equation. And they're both equivalent by that equation I have there. If you can calculate the probability of being in a zero and non-zero case, right? That's the blue underline, the probability. And that's why I'm emphasizing why probability is so important. So let's combine a couple of things. When a data scientist tries to model this imbalanced data set, they're going to want the probability. And the problem that we'll inevitably run into, the problem I ran into, is that you need to sample to improve your model and you'll distort your probability. So I'm going to show you what to do here. So let's first kind of discuss here this concept of sampling your data and why it distorts your probability, right? And I have a simulation at the top that tries to kind of illustrate this, right? I've simulated 3 sets of data represented by each of the rows here with different sets of imbalances. And I've undersampled the majority class. So just say I have 100 data points, 95 negatives, 5 positives, that's that first row. I've undersampled the negatives or the larger class. And we know what and then I fit it to a random forest and I calculated the probability. But we know what the actual probability is because I've simulated it, right? It's synthetic data, right? And that's in each of these cases. In the first row, it's 5%, right? That's what I actually generated the data with. But because we sample this 10 to 1, you can see that the random forest, this undersampled probability column, is at 9%. Regardless of my data set, it's going to be 9% because I undersample the same each time. You could see how sampling distorts your probability and you need to make a correction on this, right? And that's what I have in the last column. After you make this correction, you get back to what you expect. Now, this is something I tried to Google to find this correction. I can't find anything in the machine learning context. So I hope this helps you. And in fact, if this excites you, which I think if you've seen the problem, it will, you could skip right to the end to get the calculation details, and then, you could kind of tackle some of the problems you've been dealing with. But let's go step by step here for those that kind of want to see all the details here. And for the rest of the talk, we're going to be using this toy example I have at the bottom here. And so it's really to illustrate how sampling affects the probability and the improvement and the adjustments we make. It's all generated in a Jupyter notebook. I posted it on my GitHub. That'll be available as well, so you could just take that down and look at it. But roughly, there's 10,000 samples in a multivariate distribution and a 10% minority class, right? That's the artificial imbalance we're doing here. And to make this relevant to finance use cases, you could think of the different cases we spoke about. I listed them on the right-hand side. And just taking one example here, credit defaults, you could think of feature one as your inverse stock price, feature two is your average sector spread. And as you get more stock price, as you get larger spreads, you expect more defaults, which would be your orange data points here. Right. So this is the toy example we're going to use. And the first thing we're going to do is build a model, sample it, and see what happens. So it's really important to note that in my experience, sampling in severely imbalanced data set always improves your classification performance, right? It's one of the first levers that data scientists should experiment when they have imbalanced data sets. It seems obvious, but I often see folks missing this point. And I think the reason why is there's this expectation that machine learning is magic and it'll figure out all the nuance for us, but this isn't true. We have to do some brain work ahead of time here. And so in this particular made up example, we see, your recall goes 61%, what I have in green in the original data set. And after undersampling, it improves to 78%. Your F1 much the same. And in this case, your precision drops, right? And again, there's some made up data here, but if we had some real financial data, the performance improvement between training and test is pretty substantial in my experience. And so the art of choosing the sample ratios and how you sample, there's a lot of art to that, and that's qualitative. And maybe that's why people are a little comfortable with it. But intuitively, what undersampling gains you is a clearer view into the hyperplane that separates the clouds. So if you look on the right-hand side of this slide where we've undersampled, the distinction between the orange and the blue, the defaults and non-default, or event and non-events, becomes clearer for the model to see than on the left-hand side where you have all these noisy zeros in there, right? That's sort of intuitively what's going on. The details on how you sample and all the different techniques, I mean, you could spend hours discussing this topic. In fact, I am planning to put a lecture together on it. But for the case, for the purposes of this talk, we're actually going to skip over that. I've listed them at the bottom. I put a reference at the bottom here, a great library you use in Python called Imbalanced Learn. It's got great documentation, so feel free to go there. Roughly oversampling, what it does is it synthesizes data of your minority class. So if you have too few examples, it generates fake data to increase your orange, right? And in the undersampling case, you're taking your blue, your majority class, and you're reducing it, right? In big data, you typically want to undersample, right? And vice versa. If you have a small data, you typically want to upsample your minority class. So last slide before we do the takeaways, and I know how I'm doing on time, but I thought I would have ran over, so I spoke fast. Let's take a look at what the upshot of all this is, right? What is the effect of sampling on the probability estimations? So there's a lot going on here. Let's go through it step by step. In the upper panel, these three graphs I have here, blue means you're very highly probable in your zero class or majority class. Red means you're highly probability. You have a highly probable minority class, or let's say defaults, or your smaller class, right? And first, go from the no sampling case to the undersampling case. And what you notice, that's going from the left-hand side to the middle, you notice the finer, more nuanced contours. And what this is showing is how sampling helps create a more elaborate hyperplane. You see these little islands there, right? The model is learning the behavior around those minority class without the noise from the zeros of the majority class, right? And then second, going from the middle, the undersample, to the undersampling with adjustment, we see a shift towards blue. And essentially what's going on here is there's an adjustment to effectively account for the fact that undersampled predictions of class 0 were underrepresented, right? We artificially reduced the class 0, the majority class, and we need to kind of account for that, right? And that's what this equation does, right? That's what we have on the lower left-hand side, what I call the novel adjustment. I have the reference there that talks about this. They talk about it in the non-machine learning context, but all the math is there. I also have the math in the appendix. Take a look at it there. I highly recommend kind of just reading the first few pages of that, that paper. But essentially, it uses Bayes' rule to account for the removed samples, right? And intuitively, if you look at beta here, beta represents how much you're undersampling. Beta is 1, you know, undersampling. Your probability stays the same. The equation actually reduces to the probability before is equal to the probability that's adjusted. As you begin to undersample, beta shrinks, and you begin to lower your probability towards the majority class. That's that adjustment towards the blue. And we see that on the right-hand side here, this graph that shows basically your unadjusted probability, like what happens if you sampled and just did predict proba with your random forest, and how does that translate to your adjusted probability. And you could see that in the lower right-hand quadrant, you could easily be overestimating the probability of your positive class if you don't make this adjustment. So very dangerous to do, and you want to avoid that. Let's jump into the recap because I have no idea how we're doing on time.
3 minutes left.
So what did we talk about today? How much you got?
3.
I did perfect. So
Perfect.
takeaways. Here, the idea is, this is when you go back and you start modeling the problem, whatever you're working on in finance, the first thing you want to think about, drive a more modular approach to your machine learning solutions, right? Try to break it into subcomponents that you're trying to calculate. Always specify the final requirement. You know what you're modeling towards. In this kind of modular paradigm where you have multiple components, you typically are going to want your probability. I think 9 times out of 10 in my experience, you're going to want probability and not just your binary outcome. When you're dealing with noisy data and imbalanced data, they're kind of synonymous, you're typically going to have to sample. As a result of sampling, your probabilities are going to distort and you're going to need a probability adjustment. And that's what we talked about today. So that kind of takes away or wraps up what I was going to talk about today. I hope this all benefits you, and happily modeling a machine learning model to everybody.
All right. Thank you so much, Mike. A big virtual round of applause is, I'm sure, coming through from the audience. Everybody watching, go ahead and do some networking, and we'll see you at the next session.